In this lesson, we're going to talk about the areas of regular polygons. The first formula that we learned was the area of an equilateral triangle in relation to its side length. So we're going to call each of the sides in this equilateral triangle S. So I have S here, and S here. Well, I know that the angle measure of each of the angles, interior angles in an equilateral triangle, is going to be 60 degrees. So I have both an equilateral and equiangular triangle. And now I'm going to draw an altitude from B to AC. And when I do that, I split the triangle into two equal halves. And because I do that, I know that this angle measure is going to be 30, and this is going to be 90. So I can call now the distance, we'll call this from point E, from E to C, S over 2, because it's going to be half the length of the side of AC. Now if EC is S over 2, then I know that BE, which is the altitude, is going to be S root 3 over 2. And that happens to equal our height. So we'll just put an H here to signify that S root 3 over 2 is our height. Now we need to find the side length, and we've been given the side length, and that is just S. So the side length, or let's call it the base, or B, is going to be equal to S. Well, I know that the area of a triangle is 1/2 of base times height. So I have 1/2 of S times S root 3 over 2. And if I multiply all these through, I end up with S squared root 3 over 4. And this is the equation, or the formula, to find the area of an equilateral triangle in terms of its side length. The next formula that we are going to learn about is a formula that relates the area of a regular polygon in terms of its apothem. So here we have a hexagon, and we need to find the area of this particular hexagon. So how do we go about doing that? Well, recall that hexagon is just a sum of different triangles. In this case, it's 6 different triangles. And any polygon, regular polygon, will be the sum of a number of triangles based upon the number of sides in the polygon. So all we really need to do here is the strategy is to find out the area of one of the triangles and then multiply that by the number of sides of that regular polygon. Well, the area of one of the triangles is just going to be the apothem times half of the side. So we can write this area for this particular triangle, if this is the apothem, as 1/2 of the base, which is the side, times the apothem. Well, now I have 1, 2, 3, 4, 5, 6 of these triangles. So if I wanted to find out the area of this entire hexagon, I would say it would be 1/2 of the side length times 6 times the apothem. Well, what is really S times 6? S times 6 is really just the perimeter of this regular polygon. So if I replace S times 6 with the perimeter, I end up with 1/2 the perimeter times the apothem, which is the formula for our regular polygon in terms of the apothem. So let's take a couple of problems to work on. The first one, 19a, asks us to find the area of a regular hexagon, given that we have a span of 30. So in this case, a span is the length from one side to the opposite side. So we've got one side to the opposite side. Now we know that half the span is going to be the apothem. So I have an apothem of 15. So remember that the way we want to solve this is we want to find out the area of each of the triangles. And so we realize, if we draw a triangle here, that we've got a set of 30, 60, 90 triangles. Well, how do we know that? If we take a look at a hexagon, and we recall that the sum of the interior angles in a polygon is n minus 2 times 180, and we draw all of our triangles here, and we know that these radii are all congruent, we're left with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different angles. Now, if the equation for the sum of the interior angles in a polygon is n minus 2 times 180, where n is the number of sides, then for this hexagon I have 6 minus 2 times 180, or 4 times 180, which is equal to 720 degrees. Now, if I divide that by the number of angles that I have, which are 12, and I end up with these angles all being 60 degrees. And the interior angles, of course, for the hexagon, regular hexagon, would be 120 degrees. So I go back to my example, and I write in here that this is 60 degrees because we just figured that out. I have the apothem, which forms a right angle, and now I have a 30, 60, 90 triangle where this value, the apothem, is equal to half of the span, or 15. Now this side is the side that's across from the 60 degree side. So I know that the 30 degree side, which is half of one side length, is going to be this value divided by root 3. So let's just write the equation. I know that the side, let's just say that this side, the side opposite the 30 degree angle, is x. And I know that x root 3 is going to be equal to the side opposite the 60 degree angle, which is 15. So to solve for x in this case, I divide both sides by 3, or root 3, and I get x is equal to 15 over root 3. And I recall that in math we don't want to have radicals in the denominator, so I multiply both the numerator and denominator by root 3, or root 3 over 3, and I end up with 15 root 3 over 3, which simplifies to 5 root 3. So I know x now is 5 root 3. I can now use the formula that I derived at the beginning of this discussion. 1/2 apothem times perimeter is equal to the area of this particular hexagon. So if x is 5 root 3, it's half of the side. The entire side is going to be 10 root 3. And I have 6 sides, so my perimeter is going to be 6 times 10 root 3, or my perimeter is equal to 60 root 3. So I have my apothem, which is half the span, and my perimeter, which is 60 root 3. I can now find the area. It's going to be 1/2 of the apothem, which is 15, times the perimeter, which is 60 root 3, and this equals 450 root 3 units squared, which is my area. The next problem asks us to find the formula for a regular hexagon in terms of its span. Now I'm skipping over 19b because we're going to get back to it after we figure out the formula for this regular hexagon in terms of its span. Well, let's just say that the span of this regular hexagon is going to be called x. And so we'll call the apothem now, which is half the span, 1/2 x. And we recall that each of the interior angles is 120 degrees for a regular hexagon, which means that half of the angle is going to be 60. I have my apothem here at 90, so I have, again, a 30, 60, 90 triangle. So if my side opposite the 60 degree angle is 1/2 of x, I can figure out what this length is, again, and we'll call this, in this case, we'll call this z. And z is going to be equal to z root 3 z root 3 is going to be equal to 1/2 of x. So we said z root 3, which is the 30-degree side, times root 3 is equal to the 60-degree side. So we divide both sides by root 3, and I have z is equal to 1x over 2 times root 3. Again, in math, we don't want to have a radical in the denominator, so we multiply both the numerator and the denominator by root 3. And we end up with root 3x over 6. Okay, so we know that half of a side is root 3x over 6. We know that an entire side length is going to be 2 times that, or 2 root 3 x over 6, which can be simplified into root 3x over 3. So I have my entire side length as root 3x over 3. I can now figure out the area, again, using the same formula that I developed, of 1/2 the apothem times the perimeter. So I know that the apothem is 1/2 x. So I have 1/2 times 1/2 x times root 3x over 3. And I'm left, and I really should put this up here, I'm left with root 3x squared over 2 times 2, which is 4, times 3, which is 12. Now this value that I found uses just one side length. So I didn't actually multiply it by the perimeter. I multiplied it by one side length. So in order to get the correct value, I now need to multiply it by the number of sides, which I didn't do previously, which is 6. And I end up with a formula of root 3 x squared, and x being the span, over 2. And this is your formula for the area of a polygon in terms of its span.